like can notify like the direction. So and also if f can be chosen like freely, what's the like you can have many different values. Yeah, so what's the meaning of the value?
Yeah, so f is like something that is given. Like for example, like that example that I had with like the sphere, it's like a height function. That says like how high are you on the sphere, for example. And then you say like, okay, like how does this height function changes if I'm on the sphere and I move like slightly. Like I'm at a certain point in the sphere, and like for example, if I then go along like something that is parallel to the equator, then so if I just like go on then the function is not changing at all because like the height is like the same. But if I go further up to the north pole there, then like the function changes slightly and gets like bigger. So and that's the thing that we want to calculate. It's like how much does the function changes if I change like the points in a certain way.
Okay. And what is this word mean? Like
canonical.
Does it mean like infinity?
Like it means like something that is like what does it mean? It means that it's there without you need to choose anything. So like it's somewhere like in here it doesn't, it means just like say that you can maybe say natural.
Okay.
Natural would be maybe
okay. Thank you.
would like to give like a different way to think about that. That might also be maybe helping you a little bit. So the point is that for all x and y as a point in here, we have a projection which was the Jacobian of phi is a map from R2 into so that's a projection. And that means that every point, every tangent vector has a unique image here. So we can like take the inverse of this map. So that would be it. So that's a map that goes from this space to this space. Once we have that, we can express the chart representation as follows. The vector here x on S is, so we want to see what the chart representation is at a point x and y. And what we do is we evaluate x at phi of x and y. So that's like a tangent vector at the surface at that point. So we get now a tangent vector at that point. And now we have that inverse map here that maps tangent vectors from S into R2. So we can apply it in particular to this tangent vector. We apply that to this tangent vector. And what we get is just some vector in R2 for every x and y. And it turns out that this one is exactly the chart representation that I defined earlier. So that's maybe a different way to think about that. In practice, there's not much difference between this formula. In fact, there's no difference at all actually. And it's over construction because in order to calculate this inverse, what you usually do is you have like you take the partial derivative in x and y direction. So you need to find like the inverse of that map, and it's easy to just like plug in the 1, 0, and 0, 1 vector here, and that's exactly d phi in x direction and d phi in y direction. So in practice, there's no like this way is not like simpler by any means. It's just like a different way of writing it. And maybe I give you like a picture again to summary. summary is that we have some open subset in R2. So that's our first, and this one is one-to-one identified essentially on the image at least with some subset in the surface. So that's like the chart. So that says essentially everything that is on the surface is one-to-one, like in this particular thing here, is in one-to-one correspondence to points here. So essentially that says like under this map phi, there's no difference between this open subset here and that open subset here. Like they are essentially the same, just like related by this map, which is like a different way to say like phrasing. So it's like really just like you can think of that as essentially saying like these two sets are like identified or they are the same. And the sameness is expressed by this chart. So that's like on the level of of the surface, and then you have the first order approximation. And by that I mean we take like the first order, and that means that for the surface it would be the tangent space at that surface. And similarly here we have the tangent space at the open subset, but we know that we can identify tangent vectors of that open subset uniquely with just like ordinary vectors. So for open subsets there is not much to do, and this one is a certain subspace in R3 because we assume that our surface lives there. So this one is a linear subspace. And now the question is how are they related? And the map that relates them is the Tx y phi. So that was this map that maps from R2 into Ts from S. So it's like a linear order approximation of phi. It's like this map that is essentially the Jacobian. Of phi. So that's like in some way you can think of this T every time I write T, it means like the derivative, or it means like the first order approximation. So here it's like the first order approximation of that subset, or the first order approximation of the curved space. And here it's the first order approximation of the phi. So T is like really just like the first order of something. And this one is one-to-one, and so is this map. And that means that every like a vector field, so if I have a vector field, then I get a tangent vector in here. So a vector field is something that lives in here. So a vector field on S is something that lives in the tangent space. Because it lives in the tangent space, we can use that map, because this map is one-to-one, to map everything back into the tangent space here to get like a certain vector in R2, and that one is then x phi of x and y as a vector in R2. So this is really how you should think of that. It's like, in somewhere, this x phi what I defined as like a vector field on D, and that one gives you, under this map, which is essentially just like identification, this originally vector field on S that you had. So that's how they are connected. So you just invert this arrow. So it's like You start with the vector field there, and you take the inverse of that map, and then you end up here. So this is this map that I just wrote down here. You take x at a certain point, then you map it with the inverse of phi, and you get your chart representation. So that's the this construction over here. Okay, so that's all I wanted to tell you about vector fields and chart representation, but I have this feeling that if I now start to talk about differential forms, you get a bit overloaded. So I would like to say we make like a questionnaire now. So you can just use the next 25 minutes and ask me questions about vector fields, chart representation, and all of the stuff that was confusing. So I saw already a few people talking also in the break. So if you have any questions, just ask and say okay, can you explain again that particular thing, or what was this definition, or why was this working? So does someone has questions? If you don't ask questions, I have to give you differential forms. So you can choose either you get more input, or I can help you explain and understand things a little bit better. And there's also no charm. I remember that the first time I saw that, I was confused, I think, for a month, where I didn't really understood what's going on and really understanding it. There's some way it's nice to have that picture, and then it's in some way a bit easy, but to really understand what's going on and how to calculate with that takes some time to get used to. So I understand it might be confusing. So please do ask questions if you have something that was confusing. So for example, one question that I was asked was in the definition of directional derivative. So how, that's maybe similar to this picture here. This is also the first order approximation. So you have S over here, and then you have a function f that maps that into the real line. And then the first order approximation of that is Ts of S, which gives you a changing vector, and the first order approximation to that space. And that map gives you a map from TSS to R. So again, if you think about that as first order approximations, then that's showing you the variation of F. And if you have the way you calculate it, it's really you just imagine that it's in a small end in here. So you have a certain starting point, and then you walk with your as you're a small end, you walk in your space, and you record the value of S if you're in a small end, and then you change say, okay, how much does F change? So for example, if you have this map which just records the height, then you can say, if I'm at this point, then I get a certain height. And now if I change, say for example, I walk around the equator a little bit like that. If I walk in this direction, the height doesn't change at all, right? So if I stay on the same height of the surface, so in this case, if that's x1, then it would be a TF in the direction of x1, say at some point S. So this would be zero, because I'm walking on the same height, and then there would be no change at all. If I walk around the sphere, and I just like walk around the outer the circle. So in this case, there would be no change, but if I would move into the north pole direction, so if I change directions, then Ts of f, so it's my vector x2, then we would like move in this direction, so we get something positive. So that would be some positive number that depends, on, of course, on how fast I go in to the north pole direction. So that's what like the f is like calculating. It's like we compare this point and then we go on a different, like a little bit time step later. So in this case, you get like the same point. But if you do it with red, then we go a little bit in this direction, and then the function changes. So we get like a different point, and then we take the first order approximation as we like set in t being small. So that's why we need like different vectors here, because like the function might change in a certain direction, but it might not change in a different direction. So that's why we need the function there. Okay. Do you have any other questions concerning chart representations and directional derivatives? Okay. If that's not the case, then, or if you get some questions later, then you can always ask the TA also. But then I continue and like define at least what is a differential form. There are different ways to think about differential forms. Like one way to think of that is just like as a tool. So like you would like to calculate certain things. So that's one way. It's to think of it as a computational tool. And what it does is that it measures properties of vectors. So that's one way, like certain properties, like you think of that as like a generalization, for example, of the length of the vector. And there's a relation that we will discuss, which is saying that it's like enables integration on the surface. So integration would be something that, like you know, like you can integrate a function that depends on one variable. That's something that you learned in your first course, and you also probably know how to integrate certain things that depend on two variables. But all of that is like essentially integration over, saying, some rectangle. So you integrate from A to B, and then from like, some C and D in some other direction. So you have a function that lives on a rectangle, and then you can integrate it. But now our surface are like, you can imagine it's like curved rectangles. So it's like the question would be, how do you integrate over something that is like curved? And differential forms give you a way to calculate that. And to see how both of these properties are related, y is like something that measures certain properties of vectors related to integration. Maybe maybe I give you the motivation is namely that we call that we can have the length of a curve. Of a curve is the integral. So that's like the length of the curve, and what you see is that essentially what I'm doing here is I measure the length of the vector of the curve, and then integrate that. So that will be our trick, is in some ways how to relate like certain integrals to the properties of the vectors is essentially by saying that certain, like for example, the length is automatically related to certain like the length of the vector. So that's a bit like a hand-wavy argument why something that like measures a length of vectors is related to integration. So yeah, so that's motivation. So what we would like to do here is measure length of vectors and then integrate for some the results on the surface. Okay. Okay. So in the differential form, a summary like says like gives you a very general tool to measure things, and it's defined as the following. A one form on the surface S, and this one form is usually denoted by Greek letters, so alpha and beta and stuff like that. This is a linear map. So it's important that it's linear for each point of the surface. We get a linear map, which is denoted again as a subscript. And it's a linear map from tangent vectors of that point into R. So you can think of that as alpha gives you a prescription how to measure a certain property of a tangent vector. So defined actions on tangent vectors. And then we want like a certain property, namely that alpha s varies smoothly in S, but at the moment I will not make that precise. I will talk about that later next week. how to make like sense of this smoothness. So one more remark that here we have a 1. That refers to that we have like one input here. So 1 vector as input. So next week we will talk also about something that is called a true form that will like have like 2 vectors at that point as the argument and then gives you some number. So that will be then something like says like that vector relates to that vector in a certain way. For example, it says like they are proportional or something like that. Here we have a 1 form which is like the simplest case where we only have one argument, where we have one slot to put in. Okay. So we know that we can visualize tangent vectors very nicely by just like having arrows, right? So we can visualize tangent vectors as arrows, but what is the visualization of a differential form? The idea here is that you represent it as like parallel lines. So these are like just parallel lines. So that's like your alpha. And now we have to say what it means. We have to say like what alpha s evaluated on the tangent vector is. So if I have a tangent vector, say that's like something like this. We have our tangent vector. So this is the point s. Then the number alpha s in x is equal to the number of intersections. So in this case here we have say 1 and then 2. So in this case it would be a alpha s of x would be 2. But of course like it depends really on the vector. For example, if I have like this vector here that points like in a slightly different direction and is less long, then the intersection would be like something in between here, so you can interpolate that. So that would be maybe a same would be 0.8 or something like that. So there's like in the like of course it's not like intersecting like really, but like you interpolate linearly. So that could be a 0.8, and then for example you could also have another tangent vector which is like in the same direction as the planes. And this one would be then having the evaluation of alpha of s, which would be 0. So you can think of alpha at the point s as like a plane, as like a collection of planes that go up until to infinity, so it fills out like everything. And then like the distance between the planes and the direction of the planes really gives you information. Like if you stack the planes closer to each other, then for example if I look now double this one, then the evaluation of x with the 2f would be a 4 here, and then that one would be a 1.6 or something like that. So it's and it's important how many planes there are, but of course it also really depends on the orientation of the planes for this pairing. So if I have, for example, this vector, it relates to 0, but if I change the planes, then there would be some intersection with the different planes. So it's like really all the information is important for one form. It's really depends on the staggering, how close they are, and also the orientation of the lines of the planes. One thing that is really hard to do is that this one is really like an image at one point. So it's really like an image of the utilization of alpha s. So it's really of like a simple point. What you're So for vector fields, we have this idea that it's like a vector at each point that changes then nicely and smoothly to each point. So that's like a vector field. At each point you have a vector. So it's like natural temptation to think of that as of a differential form. Also that we have, at one point, you have certain planes, and then at another point, so that would be the planes at that point, and then at another point, you have different planes. The problem, that's the correct picture. It's like that, like at each point you have like different planes. The problem is with a vector field, you think of them that like the vector field like moves nicely. So what you would like to do is like for lines between it, right? Like you have like this integral curves, what they call it. Like you connect them with lines. So you think of that as like lines which are like smooth, nicely moving. But it's usually not correct to think of that these parallel lines here, these ones, are like in some way related. So usually at two different points you get like two different planes, but they don't fit nicely into something where you have like where you fit in nicely at different points of a nice curve. Like sometimes they might, that they fit like nicely together, and for example at that point here you have planes which are like pointing then tangent to a certain curve, but usually it's not the case that they're like very not nicely and smoothly. So they might be like staggered up a little bit like differently and don't like connect nicely to one line or something like that. So it's okay to think of that as like each point really has like a family of planes, but you don't have to form something like something nice if you draw all the planes together. So like think of them as like at each point. It's nice to think of them as really as planes, but if you think of them as like moving at different points, then it starts to get like very tricky to visualize them because you have like all intersecting planes with like slightly different orientations. So that's just like as a warning. It's like if you like sometimes it doesn't work to think of them really as like a nicely family of planes that like vary. So think of that as like different points. Okay, I know that it was quite a lot of things to take in. yeah, please review that material also and try to really understand what's going on with the chart representations. And then next week we continue with differential forms and how to integrate them and represent them in in charts also. Okay. And see you next week.
That's what all these planes generate. Just all these planes generate. Why?
Like that's just like a visualization. Like it's like the vectors here, they're also like auxiliary. Like seeing what these vectors are is the same thing here. It's like seeing what any like a data that I have like there's little canonical visual that say what these planes are, but like they depend on your definition. Visualization of like there's two ways to understand it. Like I can see the planes is the one form. Like once I give you a plane, then that's the same thing as like giving you a one form. Or you say like okay, like I have a linear map. There's one way. If I say like I give you a plane, then it's different. You're strict. Like you give me a vector, it has to be how many times I intersect it. Yeah, so there's two ways. The one way is saying once I have these more parallel planes, that's like what I gave you. And then I say like, then you ask me, okay, what is the parallel plane? So then I can say, what is the one? And then I say like, okay, when I have to tell you, what is this value? So I have to say like, what is alpha defined on the vector? And I say, okay, like I define that here, and counting the number of intersections that of this plane with a given vector. And I say that this is a number. And then I say like, okay, that number is a linear. So that defines me the one. Does this make sense? In some ways, this question is like, what is a vector, right? Like if you say like, how is that a tangent vector? It's a bit like a similar kind of question. It's like, once I give you that vector, say 1, 2, you can draw them. But like, yeah, like it's a bit like here. It's like once I give you that these planes are like the order planes which are like parallel to one. So let's make it like very easy, right? So that will be all the planes that are parallel to the y. That's like the information that I gave you. And now you have to say, okay, what is alpha? So you have to say alpha of some vector equals to some. So you draw, what you now do is you draw this vector and you calculate the number. So it's like this vector. That's 1, 1. then I calculate the number of intersections, and in this case it would be 1, 2. So in this way, alpha 1, 1 equals 2. And now we can calculate, for example, 0, 1. That would be something that points in this direction. That would be 0 because it doesn't intersect anything. And so you can construct out of the plain information, you can construct that kind of information from arbitrary vector. And that is described like a one. And it's just like interpolation. You think of that as like saying like this one is 1 and this one is 0, like this one is 1 and this one is 0, and then here would be a 0 turn A. It doesn't reach like too far, and this one would be maybe 1.6. So it's like linearly interpolated. You can't really draw, you just draw like where there is a whole line. It's like linear interpolation. So that's the so like the point is that like the problem is like a vector is like as a bullet point, right? It's like it points in another direction. So but if it has like you don't get a nice
如果我假如不是飞机长不是你下面的几个不是我先比了一个方向上，然后我的手机也是能求的。
But this definition, from the calculation, the process of calculation, I can understand, like what the definition is trying to say, but I don't understand what this part means. Like, what does the T stands for, and what this whole thing says. I'll try to look over it after class.
One second.
With the alpha S plus usually in S means that for two very close to point in a surface, the parallel line around this point and around that point, we are connected smoothly.
Yes. So that means like you have like these planes, and then at a different point you have like a different planes. But if you have the points close by, then also the planes look like very similar. It's not like that you have like this in this plane and then they move like together. But it's really like they look a bit like this.